Welcome everyone, and it's being recorded. Okay. So welcome back everyone. This is our day 3 of the plenary session. So today we're gonna roughly have a 2-hour session, and we will start by Dunyu Liu talking about some latest GMTSAR development with Python framework and the graphic user interface. Dunyu, it's yours.
Okay, thank you, Anne. Maybe I can share my screen. Great. So then I'll just start. So today, I'm Dunyu Liu. I'm a senior computational geoscientist at the Institute for Geophysics at UT Austin, and I work with Anne, David, and Xiaohua on this late development with the Python framework and GUI. So this will be the topics I will touch on. So the design philosophy of GMTSAR and Python framework and the testing system and the graphic user interface GUI. Okay. So I think a really vibrant GMTSAR community or any software community really depends on the users, educators, and developers. And the developers are critical for the future of GMTSAR. And so I think with the Python framework and on the infrastructure side of the GMTSAR, there's definitely new opportunities and for young talent. It seems, can you see the full screen? It seems my screen is blocked somehow.
Oh, we can see it. The
Okay, great.
GPU modules.
Yeah. So yes, maybe my computer issue. So yeah, this slide is borrowed from Xiaohua's talk in day 1, and really that's the sort of my understanding of GMTSAR design philosophy is the module design, and basically the GMTSAR is cut into different functions, and each function is a module that consists of submodules. And not only the design is like this, but the code, like, some module is actually individual script. And it really gives GMTSAR flexibility to expand for new functions. And so I think that's a really good design. And also we have other modules and like time series we talked about yesterday, and other data manipulation tools. And on the top level, the infrastructure level, and that's basically P2P processing and batch processing and those kind of script that manage all the modules below that. And so actually Python framework has arrived. Currently it is released in the version 6.5, I think maybe late last year. So it is in a separate folder and the GMTSAR. If you go to on the right, you see, and if you go to the GMTSAR GitHub repository, and it is all of the Python development are under this Python folder. We try to separate it from other development. And so for smooth user experience, we actually keep all the naming convention namings and usage the same as the old C shell scripts. So the only change here, for example, the top level P2P processing, .csh, that's the old one. And with the Python one, we just eliminate the CSH. So if you want to use the new Python version, if you want something new, and basically there should be not any issue. It should be smooth user experience. And so like Xiaohua mentioned, young generation scientists, they don't like C shell. They are more not maybe not don't like, but they're just more familiar with Python. And also there are a lot of strengths with Python. Like it's modern and flexible, and we can give more structures to the code. And the community support is really good, and it is more interpretable. And also with the Python framework, and we can move some redundant part away and build some kind of hierarchy in the system. It's lower cost to develop, expand, and maintain. And it is also coherent with the PyGMT development. The GMT is a really central part for GMTSAR, and the GMT team has been developing their Python framework in the last couple of years. And so the current Python framework for GMTSAR is ready to be incorporated with their development in the next step. And also it support parallel computing better. And importantly for, if you're interested in developing GMTSAR, it's a really good skill set, beneficial to developers because all the AI, data analytic stuff, they're all in Python. So here in the Python folder on GMTSAR master GitHub repository, and we have a utils folder. Basically, on the right, you will see all the scripts utilities. There are the Python version of the utilities that's available now. If you want something new, and definitely give it a try. We use the same model design, the same naming and usage conventions with the CSL utilities. But a word of warning for sure for any new development and for a complex software like GMTSAR, there must be bugs, and we'd love to hear your feedback, and if you see any bugs, and share with on the GitHub open question over there. And also let us know what new features you want over there. Currently, these are still the core function part of the GMTSAR. But if you want something new, or there are other kind of like batch processing, if you need it, and let us know, and we will put it as a priority to develop. So coming along with the Python framework is the testing system. This may be more for the developer, but I think it's really important part of the system. It ensures consistent performance for GMTSAR. Typically, if you add a new feature to a complex software, what normally happens is it may break old functionalities. That's what we don't want. So with the testing system, actually, we can ensure consistent performance. And it means lower maintenance cost to the developers. And currently, the testing system is done at a high system level. Like we have maybe 30 sample sets from Topex. Later, definitely you will interact with this website on the right. So you pick some example data sets to play with. So currently, the testing system will just, for example, you add a new feature, and then you just run over all the tests, and to compare, the new results with the previous results where you have manually examined, and make sure they are right, they are the same, and then you can pass this new feature and commit to the system. But actually, there are other, so we can gradually introduce lower level testing to the system. For example, just the test, as for example, interferogram function, the intf, that function, and you just design some smarter test, and for that function, you can do that for many functions, and so basically that will give a really strong foundation for GMTSAR development, and it will be really good for users too. It will be less bug, and save both developer and users time. So now here is the new thing. It's a graphic user interface. It happened last year when I saw my colleague his GUI for his teaching tool. I think, okay, it's cool, and maybe we can introduce something to GMTSAR. Because I know some people may more familiar with this GUI thing, not the command line thing. So this is the GUI feature. I'll show a quick demo for it. Currently, my development for GMTSAR is happening on GUI now. Basically, it will interact all the command lines, but just that this GUI provide an interface for us. So it is based on a really popular Python package. It's still Python. It's called tkinter. So it's really popular. It's not really complex, and so that's what we want. We don't want it to, for example, after another iteration of tkinter, and they change a lot, and we need to change too. So maybe let me. How can I stop sharing? Okay, so let me show you GUI on a quick example. So can you see my terminal? Let me make it. So basically, it's called a TK GUI and a GMTSAR, and it's a Python code, and I make it executable, and then you can run it. It will give you an interface to play with. So there are several functionalities, and currently still quite simple, like download a sample data set from the topics. So for example, here we have a bunch of them. And given the time limit, I will just show, I'll try to run the RS2 data set. Is an old satellite, but it's really small, and you can run it quickly. So for example, there is a drop-down list, and you can navigate the file system. For example, if I go to Python runs, and that's where I have already pre-stored all the data sets. And if I get into this RS2 folder, and you can see we have int_f. If you're in last yesterday's short course, you will know int_f will store the results. But I can clean it. And if I get back to it, you see we don't have the int_f. And now I can just config. So basically the default is RS2 satellite. You can try ALOS2 S1 tops. And then you click config, and it will give you the configuration file. And we have some toggles here, and you can choose which phase you want. And then P2P processing, and you will see all the, yeah, so basically there is a window that shows all the command lines and the printouts from the code running to this kind of canvas. Okay, so basically the GUI will throw the command lines into the back end of your system. Currently I'm using a Mac, but just to save time, and I'll go to another, for example, ALOS2. So you see we have the results here, and there are some buttons here if you have results, and you can quickly visualize, for example, this is a correlation mask, and displays amplitude and phase without filtering, and this one after filtering. Definitely we will have the unwrap and LOS displacement figures coming up too. But still under development, but I think this is a cool thing, exciting thing I want to show. Okay, let's get back to the slide. Okay, I think I'm reaching my time point. And this is for if you are interested to be a developer. I think sort of for scientific software where always we are both users and developers. And maybe two resources if you want to become more efficient in coding and developing software system, and this clean code that introduce the idea that your code needs to pass all the tests and minimize duplications and needs constant refactoring. I think that's a really good point. That's why I introduced the testing system to GMTSAR. I think it's important. It saves me a lot of time. And also there's a new talk by Andrej Karpathy, because, the AI era, and is coding may become different. So I recommend you to, if you're interested, watch this video. So yeah, these two slides are so NISAR. So based on news, arrived at the India launch site last month, and so we will have a boom of InSAR data coming from NISAR. So it's not just a great time to be a GMTSAR user, and it could be a great time to be a GMTSAR developer too. So yeah, that ends my talk. Thank you.
Thank you, Dunyu. And let's move to our next talk. And as a reminder, if you have any questions, you can utilize the Q&A and we will provide live answers. And after that, we have an active Discord channel and that we will engage and continue some discussion where you can share some common issues that you think might be an interest to other students as well. So our next talk is about GMTSAR applications on volcano. And Eric, and it's yours.
Okay, thanks a lot. Thanks, Dunyu, for the exciting talk. I haven't tried the GUI. I haven't seen that yet, but that looks really awesome, and I'm excited to try that out. It looks really cool and great for learning and kind of exploring and being able to see things really easily. Okay, can you guys see my screen okay? So I'm going to talk about applications to volcanoes. This is a little bit outside of my main work, although I now have a couple students who have been working on volcanoes. So it is a really awesome kind of application of InSAR because volcanoes have, typically mostly vertical deformation. And if you think about the line of sight coming from the satellite, it's mostly vertical. So the InSAR is really sensitive to vertical motion. So, and volcanoes, especially if they have recently erupted, tend to be covered in rocks. And so they also have good coherence compared to some other areas that might be covered in vegetation. So it's a really good application. So I thought I would just kind of show these slides and just talk about some of the exciting applications. So, volcanoes obviously are very hazardous. And they tend to have precursors, right? So they tend to inflate the magma chamber that's close to the surface before it erupts. And so in many cases, you get some degree of warning before a volcano erupts, unlike, for example, earthquakes. And so that makes it also kind of an exciting thing to conduct sort of monitoring. But beyond just the monitoring, right? If we're interested in doing scientific work, we want to understand the dynamics of the volcanoes, be able to understand, why do some volcanoes have certain types of precursors when others don't? What's going on with the magma chamber? How is it physically behaving? What are the properties there? And another aspect of it is that a lot of the world's volcanoes are in pretty remote areas, and they don't have monitoring networks installed on them. So many volcanoes do, but not all of them. And so if we want to monitor all the volcanoes in the world, InSAR is really the only way that we can do that because it's got systematic global coverage. So it's a really great application of volcanoes. Oops, here we go. So this is an example from the Galapagos. So this is a pretty early example from, I think this is ERS data, and showing these. So this is interferograms over these islands, Isabella and Fernandina. And you can see that actually many of the volcanoes on the islands have signals, right? So this one has this uplift here. This one's got uplift on the side, right? This one's got uplift inside the caldera. We lose the coherence here because this volcano has been covered in vegetation. And then this one also has uplift. And then these lava flows from previous eruptions are actually subsiding as they cool. So there's lots of interesting stuff going on in this image. It's pretty fascinating. And so what they were doing was testing out different models. So here's a MOGI model that's kind of just a simple point source. The point is illustrated in the dot. you notice that the circles are not symmetric around the point. And that's not a mistake. That's because the InSAR is viewing from the side. So a MOGI source creates both vertical and horizontal uplift or deformation. And so on one side of the volcano, the vertical and the horizontal motion will add together. And on the other side, they're going to be opposite because the satellite's looking from this direction. So you get a little bit of asymmetry in your observations. So that's one clue about a magma chamber is that usually you'll see the deformation slightly asymmetric with respect to where the magma chamber actually is. And so this was their fit to the MOGI model. This is a different kind of model where they have more parameters and they can try to estimate where the magma actually is within the caldera. So pretty exciting kind of stuff. And you can see that, at least in the coherent areas, this data is just really beautiful. It's like really clean and clear InSAR data because this area is just covered in rocks. So it's very barren landscape, which makes it great for InSAR. So in Hawaii, that's another exciting one. I don't know if you guys have been following the Kilauea eruption that's going on this year. It's been fountaining lava up to 2,000 feet or something, and pretty impressive eruptions going on there right now. This is an earlier one from 2007. And so what happened was Kilauea caldera deflated. So you see negative line of sight here, or movement away from the satellite. And then over here, there was a dike intrusion that opened and produced sort of uplift and outward motion. So you actually see kind of both of these things happening at once. And then there's previous lava flows out here that are causing decorrelation because the lava flow actually occurred in between the time that the images were collected. So you can actually use that to map the lava flows as well. So that's another application, is mapping the flows with decorrelation. So if you sort of combine the InSAR with GPS, then you can see that there might have actually been a slip event. There's a décollement below the base of the volcano. And you can see these large normal faulting scarps out here. So that's a big concern for sort of future tsunamis. And InSAR, like in the Galapagos, you can kind of map large scale areas. So this is another old study from the Andes where they were able to use data to just kind of look at all sorts of volcanoes across the whole area. And you can see they sort of highlighted all these boxes here. They didn't detect deformation in all of these, but they've highlighted the ones where there is ongoing deformation. And they were actually able to sort of surprisingly discover some volcanoes that were uplifting that weren't known to be active. So this was a great example of monitoring. And there are actually some that might be deflating as well, right? So there's all sorts of dynamics happening within magma chambers. And so InSAR is a really, really great way to kind of monitor that. Here's another one in the Aleutians. So the Aleutians are actually, it turns out you think they're really remote, but it's the main air traffic route between Asia and North America goes right over the Aleutian Islands. So if you're flying between Tokyo or Beijing or Seoul and the west coast of the US, you go right over the Aleutian Islands. And so this is an area that's really important for monitoring eruptions and ash hazards to air traffic. So the Alaska Volcano Observatory actually monitors these volcanoes really kind of routinely and carefully with InSAR. So this is an exciting one. Of course, volcanoes are a sort of a special case of topography, right? Where the topography is very pointed. And so they tend to get atmospheric artifacts as well. And I talked a little bit about this in my talk on Monday. If you have like a different amount of stratification, you can get a sort of a path delay difference that looks just like the topography on your interferogram. And so it's actually not a topographic error, it's just a difference in the path delay that's proportional to topography because of the atmospheric noise. And sometimes what you get is something where it's like more stratified on one side of the volcano and more turbulent on the other. So this is actually a model that they're trying to use to correct this interferogram. But you can see that the model doesn't work perfectly. For one thing, the model is much lower resolution. And this is still the case. This is a little bit older, but our models are still like the ERA5 is at quarter degree resolution, I think. So that's 25 kilometer resolution. But InSAR is at 10-meter resolution. So there's a mismatch in our ability to really monitor the atmosphere at the scale of InSAR. So we still don't have perfect atmospheric models. And so that's always a challenge. And it can be especially a challenge with volcanoes. I think I showed this one on Monday. So this is Mount Agung in Bali, and this interferogram looks really concerning, right? It looks just like a big deformation signal, and it's happening at a time that there was a seismic crisis. So we think, okay, there is magma intruding somewhere on the island, but we don't know exactly where. The locations of these earthquakes weren't really great because the monitoring network isn't very dense. So we're trying to figure out where is the magma going. And we see this interferogram and we're like, oh shoot, it's right underneath Mount Agung. That's really bad. But it turns out this was just atmospheric noise. And one clue here is that it looks very symmetric. If there was magma intruding below the volcano, it would actually be producing an asymmetry, and you would expect that bullseye pattern to be shifted a little bit off center from the volcano. And in this case, it was very symmetric. So it turns out that we decided eventually we were looking at this in real time. I remember sort of sitting there late at night trying to decide what should we do about this, and there were people posting on Twitter this interferogram saying, "Oh, this is really concerning." So eventually we decided it's not like a massive magma intrusion. There might be a smaller one that's within the noise, but we can't tell. And it did erupt. So it was an eruption, but it was a relatively small eruption. This doesn't look that small, but the fact that the lava flows aren't making it down the sides is what was important here for the hazards. It's kind of a beautiful eruption. You have steam on one side and ash on the other, both at the same time. Pretty amazing kind of two-color eruption. So here's another example that I had showed before. I just want to really emphasize this issue with the topography and the atmospheric delays. This is an atmospheric delay that looks just like topography. So just like the Agung example, this is actually atmospheric noise. This is also atmospheric noise, but this one looks much more turbulent. So there was sort of more airflow around the volcano. And one thing that you may notice, so the satellites, if you think back to David Samuel's talk, the satellite is in a sun synchronous orbit. So that means it always visits the same place on the Earth at the same time of day. So the descending satellites, I think, I might have mixed this up, but I'm pretty sure the descending satellites always visit the same place on Earth around sunrise. So that means if you think about the sun and the Earth, and the sun is pointed toward the Earth, the satellite is just going around, right around the sunrise sunset line, so that it's always on the sunrise sunset line, and then the Earth turns underneath it. So wherever the satellite is, it's always observing somewhere on its descending path that's around sunrise time, and on its ascending path, it's around sunset. So that means that if your weather tends to be calm and clear in the mornings, you might get more stratified delays in the descending data. And if your weather tends to be turbulent and you have thunderstorms in the afternoons, then you might get more of this turbulent atmospheric images in your InSAR, in your ascending images. So if you look at that ascending time series and a descending time series from the same area, you might tend to get these kinds of differences that are systematic between the two. So that's certainly something to watch out for. And it also means that you can check if you have ascending and descending data from the same volcano. One way to figure out if the deformation is real is to look at one or the other, because one of them might be stratified and the other one might be turbulent. So then you won't be able to see you might see different noise patterns in those two images. And of course, you can always see this type of deformation that looks just like a volcano, but this is actually just a DEM error. So this is another common one that happens to people if your DEM correction failed and a tile was missing in your DEM, or it was accidentally set to 0 or something like that. You may see these fringes that look like a volcano, but it's just topography because the DEM correction failed. So, okay, so I have an example sort of from the 2018 Hawaii eruption. So these are put together by a whole team of people who are not me. So Xiaohua, Bridget, and another team of lots of other people who were monitoring this 2018 volcano in Kilauea, this eruption in Kilauea that was going on there. So it was a pretty exciting eruption. There was lots of different lava flows that happened over time. And it was kind of a hazard of really concerning to people because it kind of had lava flows that covered some houses. So processing was all done during with GMTSAR using kind of the modern updated methods like the geometric alignment. They aligned everything to one scene. And then they did mostly short time span interferograms in order to try to keep the coherence good, right? So this is using the Sentinel-1 data from 2018. This is kind of a map of the lava flows that have happened over time. So Kilauea is up here. This is called the Lower East Rift Zone, and it extends down here, and you can see the Leilania states. This is an area that got kind of damaged by this eruption. So 2018 is the eruption here in blue. So this is the areas that were really concerning. I think my arrows, these red arrows are a little bit off. They're supposed to be pointing at Leilani Estates here. So this is where the venting started. It just erupted right in the middle of the housing district. And then the lava flowed downhill. So here you can see, this is the descending time series. So they made both ascending and descending. And so you can see that this deformation basically is reflecting deflation of all of this area. So the deflation is happening because the lava is coming out to the surface, right? So the magma was already there in the rift zone, and now it's coming out. And so it was deflating both from the caldera and the rift zone, and it just continued sort of deflating over time. So here's a set of sort of profiles across that. So you can see each one of these is a time series slice through the data. So you can see how the deflation just continued on. So there's actually a rapid deflation right at the beginning associated with this larger earthquake, and then it continued deflating over time. There was a little bit of intrusion in this one spot, so maybe it actually uplifted there. So it's kind of interesting. But the rest of it is all deflating. And so this is sort of an effort to model where these volume changes are occurring. So try to model where the magma chambers are at depth. You can see this is actually relatively shallow, right? It's all above 4 kilometers of depth. And so you have the large magma chamber beneath Kilauea caldera that's deflating. And then you also have sort of both inflation and deflation happening along this rift zone. So you can try to estimate the amount of volume. So there's about a cubic kilometer of material that was lost from the magma chamber at the summit. And so that agrees pretty well with the LiDAR mapping of the deformation. It does not agree that well with the MOGI source. So MOGI has some issues. And I actually have a student who's working on a similar problem, trying to compare these different types of models and understand how they compare. Here's another kind of crazy one. So this is a mud volcano that erupted. I believe this is in Azerbaijan. So so mud volcano is a different type of volcano that can be driven by gas pressure within the earth and other types of things. So I think they're flaring this gas off to prevent it from becoming a hazard. It looks kind of worse, but it's better to have CO2 than methane in the atmosphere. So if it's going to be doing that, you probably just want to burn it. And you can see that here there was this sort of a big subsidence and an uplift at the same time. So it's kind of a different application, but in the same sense, you have this vertical motion. So monitoring that vertical motion is really a good target for InSAR if you want to understand the volume changes, et cetera. And then the last thing that I wanted to highlight is there's been a lot of work, if we're thinking about monitoring volcanoes at a fairly large scale, there's hundreds, if not thousands, of potentially active volcanoes around the world, and it would be really hard to monitor all of those in real time every single time there's an interferogram. It would just be a full-time job for many people. And so what this group was doing was trying to figure out a way to use machine learning to detect volcanic deformation. So they have some data. It's doing this sequence of things. So it's trying to identify the edges, separate the background from the volcano areas, and then they feed that into a convolutional neural network, and they train it on a set of data that they know is real deformation. And then they can pass it through. Now they can pass through new data and test on whether it's able to detect the volcanic deformation. And so their results look pretty good. So this was actually, I think this was maybe one of the first studies done on this, but it really works pretty well. So they were able to say like priority is like, probability is relatively high here in this area that there's a volcanic deformation, right? So in these are examples of their successful cases. It wasn't 100% successful. Sometimes it missed the volcanic deformation, or sometimes it got confused, right? You still don't know if this is real deformation or if it's maybe just topographic noise related to the stratified atmospheric delay or something like that. But at least it helps you to sort of identify a few smaller set of interferograms that you should look at. So I think this is a pretty cool example of machine learning applied to InSAR. So we're not really modeling it directly with the machine learning, but we're using it to prioritize which interferograms we can look at. So just to sum up, then InSAR is really useful for volcano monitoring. We definitely have to be really careful with atmosphere because it can be really correlated to the types of signals that we expect to see in volcanoes. Sentinel is awesome. It's free data. The repeat times are pretty good. The orbits are pretty good. But even when we have InSAR data that's really good, we always would like to have other data that we can compare it to, because sometimes the modeling isn't going to be as accurate unless we have really that ground truth data. So that's all I have. Thanks.
Thanks, Eric. And we will have one more session on the InSAR application for earthquakes and the post-seismic deformation. And after that, we are going to take a 10 minutes break. Kang, it's yours.
Okay. Hopefully I don't mess up the slides today. Do you see my screen?
Yes, right now it is.
Okay.
Yes, we can see
okay.
it nicely now.
Okay, good. Hi, this is Kang Wang. I'm a data scientist at Earthscope Consortium. So in this presentation, I will show some examples of how InSAR can be used to study the ground deformation related to large earthquakes, including the deformation during the earthquake, as well as deformation after the earthquake, which we call post-seismic deformation. As we just saw in Eric's talk, InSAR can be used to study, volcano deformation. And in this presentation, I'm going to show InSAR is used for ground deformation of earthquakes. And you will probably have seen also applications of InSAR to map deformation in other geological or engineering settings. And it's actually, in fact, this InSAR has been widely used to map all kinds of deformation, ground deformation in different geological settings. But probably one of the earliest, if not the earliest, application was the mapping of the surface deformation associated with the 1992 landed earthquake, as shown on this interferogram. Because of its pioneering significance, this work was featured in Nature, making a major milestone in the development of satellite geodesy and demonstrating InSAR's potential for precise and large-scale ground deformation mapping. Now, 30 years on, InSAR has been routinely used to study ground deformation related to large earthquakes, enabled by significant progress in satellite mission, data accessibility, and efficient processing algorithms and software packages like GMTSAR. So here I show an example of recent effort using InSAR to look at the deformation of earthquakes. I'd like to invite you to pay attention to the time here. So this is an example of the 2023 earthquake doublets in Turkey. So the earthquake occurred on February 6th, but you can see that nearly after 2 days, there has been posts of the ground deformation mapped by various satellite missions, including ALOS-2 as well as Sentinel-1. So this is pretty quick. It's only like hours after the earthquake, or even at most even days, at most a few days after the earthquake. And in fact, there has been a statistic to show that InSAR, especially InSAR Sentinel-1, has been successfully used to map deformation related to earthquakes above magnitude 6 also around the globe. This is a slightly outdated map, but you get the idea. So given how far InSAR has come, the natural next question is, why do we study earthquake deformation in the first place? And more importantly, what unique role does InSAR play in terms of helping us understand the geological feature of the surrounding area? So first of all, we may simply want to know the detailed surface deformation caused by an earthquake. That is, how much the ground has moved and in what direction. And this provides us essential insight into the rupture process, fault slip distribution, as well as the geometry of the fault at depth. So here I show one of the early examples of using ERS InSAR, ERS data to map the complete 3D surface deformation surrounding the Hydrology earthquake in Mojave Desert in California. So in addition, on top of that shows the traditional landside deformation derived from InSAR. In addition to that, you can also use the amplitude information to map the deformation along the azimuth direction, because as we know, the InSAR is only sensitive to the landside deformation. So to get the three-dimensional deformation, you need a cross-track measurement, which is often done by a method called pixel tracking or cross-correlation, subpixel cross-correlation. The idea is that you cut the image into many patches, and within each patch, you compare how much the pixel has moved with respect to the first image or reference image. And when you combine the pixel tracking result with the landside deformation, you can derive a very detailed three-dimensional deformation field. So this is one of the early examples, and you can compare the results with the GPS observations that they match the GPS pretty well. But keep in mind, GPS is only sparsely available. It's only available at very limited sites back in the early 1990s. So InSAR is very complementary here, and that plays a critical role by offering dense and spatially continuous measurements of ground deformation over a wide area, something that traditional GPS or field observations cannot provide. With the detailed surface deformation mapped by InSAR, along with other geophysical observations, including, for example, seismic data and GNSS data, again, we can begin to model how the earthquake rupture propagated at depth and estimate the distribution of slip at depth, as well as probably, to infer the physical properties of the surrounding crust. And this is typically starts with a process called finite fault inversion, where you simplify the fault as a plenary fault as a plane, and you infer how much slip is occurring on each patch of the fault. Those models can help us understand the mechanics of the faulting, assess the stress changes on assessing the stress changes that may trigger future earthquakes, and improve our understanding of the seismic hazard, especially regional seismic hazard, because you can, based on the model, you can compute how much stress has perturbed on the surrounding regions, especially on the faults that you think might be potential for future seismic hazards. This type of analysis is now routinely performed for almost all major continental earthquakes above a threshold magnitude, as I just demonstrated in the last slide. So thanks to the global availability of high-resolution SAR data and rapid processing techniques. However, it's important to also recognize that such inversions or inferences is often subject to large uncertainties. Here, I show an example of using both InSAR and other geodetic data and seismic data to try to constrain the slip distribution of the ridge crust earthquake. As you can see, this earthquake, the rupture was well imaged by InSAR and other seismic and the geodetic data. But if you look at the resulting slip distributions proposed or published by different groups, you can see that the difference is very significant. There are large uncertainties. So just to give you an idea, this is a pretty non-unique. So although there are some uncertainty, there might be some uncertainty in the exact details of the slip distribution. The fundamental process is well understood. That is, earthquake release strain that has accumulated over years or even 2 centuries. This concept is captured by the so-called elastic rebound theory, which provides a simple but powerful explanation. That is, the stress built up along the fault before the earthquake, and when earthquake occurs, the stress or strain reduces. And if you measure a point close to the fault, you will see that the displacement increases with time until an earthquake occurs, and then it drops back. However, the rebound only marks the beginning of an earthquake cycle. What we often see is that in a time period after an earthquake, there was often a time period during which the deformation rate is much higher than the interseismic or the deformation before the earthquake. So we give it a special name called the deformation occurred during this time period is often called post-seismic deformation. Basically, it's just a special term in the context of earthquake cycle. So what causes a post-seismic deformation? It turns out that there are several mechanisms. One of the commonly considered mechanisms is called afterslip, which refers to the aseismic slip. Aseismic slip meaning that the slip occurs on the fault but does not generate seismic waves, does not radiate seismic energy. Oops. And this is called afterslip. Depending on the frictional properties on the fault, the earthquake typically occurs in areas surrounding the coseismic rupture area. Another key process is called viscoelastic relaxation, which involves the flow of the warm ductile rocks in the lower crust or upper mantle. And in addition to those two processes, there's also a process called poroelastic rebound. This happens because our Earth's crust is porous. It contains pore space. It contains water, basically. When the pressure inside the pore space changes due to the earthquake, it has to be rebalanced. So that results a lot of observable surface deformation. It's called that deformation due to poroelastic rebound typically occurs over a shorter time scale, but it can be seen by InSAR as well. Clearly, starting the evolution of the post-seismic deformation allows us to kind of distinguish those deformation processes, and also they help us understand the mechanical properties of the surrounding crust, the fault zone and the surrounding crust. For example, in the case of after sleep, post-seismic deformation might be used to study the friction property of the fault, and in the context of viscoelastic relaxation, post-seismic deformation might provide insight into the rheological properties, especially the viscoelastic properties of the lower crust or upper mantle. And in the case of poroelastic rebound, post-seismic deformation might be used to infer the hydrological properties of the crust. So next, I'm gonna show several case studies where InSAR was used to monitor post-seismic deformation and to investigate the underlying mechanism and the mechanical properties of the Earth's structure. I have to say that most of the examples I show here are based on my own work. I choose my own work because I'm most familiar with those of those studies. But you can find similar studies for different earthquakes. I'll start with the upstate case. So here it's the Gokha earthquake. Gokha earthquake occurred in 2025 along the central Himalaya. And the post-seismic deformation of this earthquake was pretty much well mapped by ATLAS-2. And based on those data, you can derive the post-seismic sleep model as shown by this black contours. This is just one of the models. But in this study, we used Sentinel-1 data 2 years after the earthquake to see how much deformation has occurred. And what we found was that after 2 years, there was substantial post-seismic deformation occurring at the down deep of the post-seismic rupture up to a few centimeters, as shown by the red color-ish patches. And with the data, we inferred that the deformation 2 years after the Gokha earthquake was nearly dominated by after sleep, which takes place primarily at the down deep of the post-seismic rupture. And we also infer that the up deep portion of the main Himalaya thrust remains locked. By locked, I mean it's not moving after the earthquake. The example I'm gonna show is the earthquake that took place in 2017 along the Zagros mountain in Iran. Again, we found also substantial surface deformation after the earthquake. In this case, the deformation 1 year after the earthquake was up to about 10 centimeters. And interestingly, we found that the deformation occurred both up deep and down deep of the rupture. So the earthquake dips to the east, almost to the east, and you see the major deformation, post-seismic deformation occurs to the west of the rupture, but also you also see some deformation to the down deep. When you model that, you will see that the rupture, both at the up deep and down deep of the rupture, there are significant seismic slip or after slip, and this matches well with the rate and state after slip model, which is governed by the frictional rate and state of frictional law. So next, I'm going to show an example of using InSAR to study the polar elastic rebound. This is again earthquake, the ridge crest earthquake. So here we used InSAR from different looping geometries along both ascending and descending tracks of Sentinel-1. We are able to map out both the horizontal and the vertical deformation after the earthquake. Here on the map to the left, it shows the vertical deformation. And if you zoom in here, you will see that there was a significant uplift around the main shock epicenter. This is the main shock epicenter. So there's some significant uplift here, as well as in the area around the 0.4 shock and 7.1 main shock. So we interpret those deformation, or those vertical deformation, is mainly due to polar elastic rebound. I will skip the detail, but just we have done pretty careful cleaning up the data and also explanation. We think those are primarily due to polar elastic rebound. And when we combine the polar elastic rebound modeling, assuming different hydrological properties, we also try to estimate the hydrological diffusivity. Basically, it's a parameter that controls how fast the fluid migrates through time. So I'm gonna skip the numbers, but just give you an idea that polar elastic rebound data, surface post-seismic deformation due to polar elastic rebound can be used to also estimate the hydrological properties of the hosting rocks. Lastly, I'm going to show an example, one of the early examples of using InSAR to study the deformation due to viscoelastic relaxation. Why are people interested in viscoelastic relaxation, particularly the earthquake in the Tibetan Plateau? Because there was a debate on whether the uplift of the plateau was driven by deeply rooted thrust faults around the plateau or by injection of the low viscosity material in the lower crust. By looking at the deformation after the earthquake, we can infer the hopefully when you tease out the deformation from other processes, you can hopefully estimate the viscosity of the lower crust. In this case, they found that the deformation a few years after the Mai and the Mai earthquake in 1997 can be explained by viscoelastic relaxation with a viscosity in this range, basically. Of course, you have to remove the deformation from other potential contributions like upslip that we have seen before. But anyway, so this can be post-seismic deformation can be used to estimate the viscoelastic relaxation, viscoelastic structure of the lithosphere surrounding the rupture. The last example, which is not often considered, is called dilatation recovery or fault zone collapse. The idea is that there was some open up during earthquake because the fault zone is pervasive of cracks or other microstructures, and when the stress changes during earthquake, the fault zone opens up, causes some dilatancy, and after the earthquake, the fault zone will collapse or recover. Basically, that's the idea, or compact, in a simple terminology. So in this case, they found that in 2023 there were some after the BAM 2023 BAM earthquake, there were significant surface subsidence along the fault that ruptured during the earthquake, and they also, combining with a model, they were also to explain how much compaction that might have occurred on the fault zone, or along the fault zone, I should say. So that was a quick overview of the examples that where InSAR was used to study the post-seismic deformation. So to conclude, InSAR is a powerful technique to study the deformation related to larger earthquakes, including post-seismic and the post-seismic deformation. And also, the recent SAR missions provides us high-quality data in near real time and enabling us to rapidly and timely respond to seismic and other hazards. With that, I'll stop here.
Thank you so much, Khan. I think we're gonna have a break and probably return at 12:15 a.m. PT, ET, like Eastern time. So then we can have a start right at 15 minutes after the hour. I'm gonna bring up a slide. Welcome back. So our next speaker, and I would like to verify. Okay. I see you. Our next speaker, Wojciech, and he's gonna talk about InSAR application to fluid.
Thank you, Anne. Could you allow me to share my screen because I think
I'm gonna stop sharing. I see you.
Yeah, of course. Thanks. Okay. Okay, just a second. Okay, so can you see my presentation and hear me?
Yes.
Also?
Yes.
Okay, great.
Excellent.
Okay. Hi, everyone, once again. It's great to be here today with you, so I think we can start. So from the beginning, my name is Wojtek Milczarek. I'm from Department of Geodesy and Geoinformatics, which is the part of Wrocław University of Science and Technology in Poland, Europe. And today I will discuss or present to you the application of SAR data that we can use in the infrastructure monitoring, first of all. And this will be the second part of my presentation because it was the same last year. The first half of the presentation will be focused on hydrological uses of SAR data, and this part was prepared by Wes Neely, and he is also an instructor of GMTSAR. So I make some presentation by him, So I will present him material shortly and then move on my own case studies. So yeah. A second. Oh, yeah. Okay, quick agenda. As I said, hydrology and crustal fluids will be the first part. After that, we go to mining tremors, which is the things I'm playing with each day, particularly. So after that, we go to time series, InSAR over active and abandoned mines. So here I would like to present to you how we can use also S1 satellite ICAVs to recover long-standing patterns of subsidence and uplift also. After that, we go to something which I think is quite new. I mean, merging SAR, InSAR data with machine learning. I would like to show some case study that we made in also mining sites. And I finish with the critical infrastructure monitoring. That will be other examples. Here I will present two fields examples illustrating how SAR data support decision makers responsible for dams, for example, pipelines and urban assets. So this is the agenda, and I would like to notice something, in my opinion, very important. Throughout my talk, you will be noticed that the GMTSAR handles most of the pre-processing and interprogram generation, while GMT renders figures and animations also. So well over 90% of the graphics you will see were produced entirely with this open source environment. Okay. Yeah. So first part, hydrology. So here we're talking about some hydrological applications of InSAR. These slides focus on groundwater, but much of it can be applied to other crustal fluids, such as oil and gas, which will be similar with my work. So I think will be very interesting. Some introduction. To start, let's talk about aquafilter system. Aquafilters are reservoirs that hold groundwater and supply roughly 1/3 of global freshwater demand. Aquafilters can be found all over the world. They come in many sizes and can be composed of a wide range of geology, including unconsolidated, alluvium, sandstones, carbonate, or also metamorphic rocks. So in the context of climate change, these water sources have become even more important as surface of availability becomes less stable. Okay, here I'm really only going to focus on unconsolidated aquafilter systems, as this system typically exhibit higher magnitude displacement associated with change in groundwater levels. So we can detect this in using the SAR data or base SAR data. Here is an example of two-tier aquafilter system. So we can see one and second, overlying a deeper confined aquafilter, separated by aquitard. Yes, we can see aquitard here. Due to higher permeability of hydraulic conductivity, pore water between coarser grained materials such as sands and graves constitutes the aquafilters. Finer granular materials such as clays and slides make up our aquitards, which helps create confining, condition, and pressurize the pore water. So when we talk about groundwater level, it's usually in terms of head, yes, head, which is the water liquid pressure above the vertical datum. In unconfined aquafilter, the water table and heat are be the same. Surface deformation in response to groundwater withdrawal is governed by Tertiary effective stress principle. So here we have on the left side and the right side two cases. So for the left side, when hydraulic head drops, pore pressure declines. In this time, effective stress rises, and the sediment skeleton compacts, generating subsidence observed from example from the space using SAR data once again. So when head rises, the opposite occurs, pore pressure increases, effective stress diminishes, and after that, the ground rebounds upward. So we have two cases of this situation, and here we have the examples, two very nice and with long history. So some of the areas InSAR application actually focus on subsidence related to groundwater pumping. Yes, here in example is InSAR over Las Vegas in the left side, showing up to 20 centimeter subsidence between 1992 and 1997. We should know that is not wrapped phase, but rather the encyclical color scale. Las Vegas is a very arid climate and has limited access to surface water, which is obvious. The needed for additional water resources to support is growing, and tourism economy has motivated increases in groundwater extraction. However, that subsidence is relatively small compared to Mexico City, yes, in the right side of the slide. This now date map shows upward to 2.5 centimeter baht per month. And I believe recent estimates have values closer than 50 centimeters, half of the meter per year. So this is the massive population. There is the massive population, and the city is located on the former lake bed rich in clay. So in the right side, in the middle, we can see what looks to be a well or maybe fire hydrant. I don't know. Maybe fire hydrant will be too high. The surface elevation in 1936 was roughly 8 meters than 2013. Yes, which is very interesting. Okay, we go next. Okay, once again, short introduction, because now we will talk about coastline and how we can use InSAR to monitor this part of this type of area. So nearly 40% of global population lives with 100 kilometers of the coast, meaning there's a lot of coast cities, Large concern of climate change is raising sea level between 1 to 4 millimeters per year. However, coastal subsidence due to groundwater extraction exacerbates the sea level rise problem greatly. So the risk of flooding and inundation becomes much higher. So Identifying these locations are critical to protection of citizens who live there. It's obvious, of course. So someone asked about coherence, the data for hydrologic application. So here's an example of Hurricane Harvey in Houston. Using a combination of SAR and other imaginary data, the authors of this publication estimate the flooded area as the blue dots in the lower panel compared to the FEMA. And the FEMA is, because as you probably noticed, I'm from outside the United States. So the FEMA is, I had Federal Emergency Management Agency. Emergency Management Agency. So this is the, compared to the FEMA results, flood risk assessment, the SAR showed many more places flooded than what FEMA predicted. Yeah. So this is another interesting application of the SAR data. Okay. Okay, so agriculture. Yes, agricultural subsidence. So another interesting thing. In addition to this map of urban subsidence, the largest displacement magnitude signals is related to groundwater can be found in agriculture production centers. So there is an example in California's Central Valley. This is an unconsolidated alluvial field aquafilter system with an abundance of clay, plagued by intense of persistent droughts over the last several decades. The region can experience up to a third of a meter of subsidence per year due to groundwater extraction. There is also hydrocarbon production scattering throughout here as well, which I will be talking about, I think, 2 or 3 slides more. So here some short summary. So Sentinel-1 mission have enabled to construct detailed displacement time series, which will play a vital role in monitoring groundwater resources for sun stability efforts, which is also obvious. Seasonal signals in groundwater dynamics, yes? With this detailed time series, we can start to look at shorter period signals, such as seasonal displacement. Here in the slide, if we just fit a sinusoidal function in our time series, we can estimate the seasonal amplitude and timing of peak uplift. Just a second. They may tell us something about pumping or recharge behavior that we could not see in the rate maps, yes? Another example will be also, half of this example will be also with California. Please, I can see my slide now. Yeah. Okay, I see. Okay, I see. Okay, hydrocarbon production. Oil and gas production can result in similar subsidence signals, but are often much more compact in the spatial extent. This is a very similar situation when we will compare, when I will show you about the mining tremors, about the spatial extent. These two examples are also in the Central Valley. If you look at the figure underneath the signals, you will find those oil and gas fields with thousands of rings. The top one is very interesting because you can see even how sharp of boundary the subsidence feature has, which is the fault action of the trap. On the right is another example of subsidence related to hydrocarbons, but in Texas, near New Mexico City. What more? Okay, elastic loading. Here I want to quickly discuss elastic loading, as this process behaves opposite to pore elastic deformation that we talked here and previous presentation also, I think. The idea is that the water or snow is loading the crust, that deflecting it downwards. When that load is removed, the crust rebounds and also after that uplifts, which is obvious. This is becoming a popular technique for estimating terrestrial water storage anomalies, particularly with GNSS measurements. However, it can be done with the InSAR, as this example of Lake Mead shows. We can see the lake in rank by deformation and And if we look the time series of the lake water level elevation versus loss signal, we see that they are highly correlated. As lake levels go up, the loss loss results, yeah, and the levels feel also the losses decreases. Yeah. I think it will be the last part of this presentation, this part of my presentation about. I would like to talk about signal superposition. It is important to remember. It is very important that deformation signals are often superimposed. You can have hydrologic, what else, tectonic, and also volcanic signal all occur in the same place at the same time. So we don't have this in Europe, but I suppose we can do something configuration in North America. We can see groundwater subsidence within the larger field of tectonic motion here. Additionally, multiply deformation mechanisms can occur simultaneously for the same processes. For example, the removal of groundwater can cause poroelastic subsidence as well as uplift from elastic unload. Yeah. So now we are going, we jump to Europe, yes, and unlike tectonically active areas, Central Europe experienced minimal natural seismic or volcanic deformation. So here, consequently, decades of underground and open pit mining, deep natural gas storage, and high volume groundwater pumping have left a legacy of man-made ground movements. So we also call like anthropogenic. InSAR, in this case, here InSAR is uniquely positioned to monitoring these processes over vast areas at low cost. This is also very important. Yeah. So first examples will be related with mining tremors. Mining and inducted earthquakes. This here we have some small area in Poland, which we call in Legnica Głogów Copper district. Here we have many mining inducted earthquakes, but the magnitude is between 2 to sometimes to even 4.5. Although modest in magnitude, their shallow foci make them relative for surface level hazard assessment. InSAR can be detect former ground deformation, provided we address two challenges. Yes, this is more, yeah, the two challenges. First of all, small special footprints offer not more than few square kilometers, and seasonality, low coherence due to the lush summer vegetation. Yes, and here probably, yeah, so here we have some examples. So when we talk about this slide, when we talk and see this slide, we can add the question. So it is possible to detect the effects of mining shock on the surface. In my experience, yes. My answer is yes, definitely yes, but always is however. Yes, however, one should take into account the limitation arising primarily from the size of such impacts, which really exceed an area of several square kilometers, not exceed. Another important factor is that I said just a couple seconds ago, consider the vegetation during the summer. So the interferogram from S1 data show high levels of noise during this period. So here we should have example. Yes, we have examples. So this is not this is the RAP phase. So this is not such beautiful like true earthquake when we have large loss signal. Here we have also RAP phase, but no, we don't have scale here. But you have to believe me that the signal in loss deformation signal loss is it's something like 600 meters to maybe more than 200 meters. So it's really small, but we can detect it. Yeah. What we can do with when we have more independent archives of S1 data. So I think it was talking the first day, by focusing ascending and descending track loss vectors or combination SAR data and GNS results, we can compute 2D or even 3D displacement field. These in turn yield curvate, till, and horizontal strain maps, which is very important for mining legislation uses to classify zone as low, medium, or risk or high, risk for structural damage. From the point of view of the protection mining sites, the possibility of determining indicators describing the behavior of the subsidence basin on the basis of SAR data is extremely important. And also in here, it will be my opinion that under certain condition, it can be used and apart with the classical geodetic measurements. I mean, I'm thinking about the precise leveling. Okay, so now we're going to time series analysis. The next example will be related to the use of time series. So what do time series analysis? I mean, when I will talking about time series, I mean SBAS mostly. So what do SBAS time series analysis actually enable us to do? So if we look at it through the prism of mining deformation, it's clear that such analysis of unprotected opportunities to describe the effects of mining on the ground surface, yes? And in the other words, if we look at it in such a way that now we every 6 days S1A, SN1C, we can obtain the result of surface displacements for an area of 10 of thousands of square kilometers, yes? And this is also power or SAR data, yes? And here we have some animation I prepared last year to you. For the left side, we have after the composition, we have two vertical displacements, and the right side we have horizontal displacements in the same mining site in Poland. So I think it's quite interesting. So we can animate when we select, for example, one of these subsidence row. We can check and animate in time how this area is building. I mean, where the mining activity was, and how quickly we can see the influence of mining exploitation on the surface. We can analyze and make classification of the acceleration and speed of mining activity on this area, which is, in my opinion, which is very, very interesting also. So another example, so I think we can move forward. We have another example. This time we are talking about S1 data with machine learning. So what we did here with my colleague, we merged of 7 years SBAS displacement with gradient boosting and LSTM networks. And what next? Training consumed roughly 75% of this time series, and the rest we validate, use the remainder. So what we get, sorry. We get 100-day look ahead forecast that outperform naive linear exploitation, and also flag zones where subsidence could accelerate toward critical threshold. Yes. Here we can see some example of our work. Yeah. On this side, we see the results of the prediction made. In the displayed graph, the blue curves indicate the predicted loss motion. Black marks show actual observed withheld from training. The close arrangement, especially during nonlinear acceleration, demonstrate that the algorithm's ability to take priori deformation history and auxiliary variables to predict future behavior. Another example with what? With shape. On this slide, we use the Shapley additive explanation method. We use it to, and we check that it could be allowed to select those variables that had the major influence of the surface displacement. In this particular case was it was very interesting because it was salt layer that we not expect that it will be this particular geological layer. We enrich the model with geological layers, aquafilter properties, and the rate of mining progress. Sharp values rank the contribution of each feature to predict displacement and in this study the thickness of the underlying salt extracted the strongest control of the surface displacements, which was later, which is also interesting, which was later confirmed by hydromechanical simulation. Next example will be, this will be very interesting and very important. I mean, not only in Poland, but also in entire Europe. We have something like we call post-mining areas. The phenomenon of post-mining deformation is most related to the reconstruction of aquifilters in the post-mining period. Yes. So assume that we close the mine, and what next? Yes, what with the water inside the ore? Under certain condition, previously excavated rock mass as a result of the reconstruction of water condition can expand. And what next? And we can observe uplifts of the surface, which also we can catch by, for example, S1 data. Why this phenomena is, from our point of view, is important? Because, as I mentioned at the beginning, most of the post-mining areas in Poland, but not only here, but also in Germany, France, or UK, are located adjacent to or in urban areas. So that's why it's very important. So what we have here in this example of the Western Poland is the different mining site, but close that the previous one. We use the archives of multipliers mission, areas 1 and 2. So 90s last century, and VSAT, and also S1 data to track surface uplift over 3 decades. Such long baselines reveal decade-long uplift trends that could be missed in the signal mission analysis. Yes, it is also obvious. Based on the analysis of SAR data, the relationship between aquafilter recovery and surface displacement was identified, which was very nice. It was the first work here that we did with Sentinel data. Another example will be from France and German. And this is from the German-French border region, and here too, also like in Poland, on the basis of the SAR time series analysis, the phenomenon of uplift of the ground surface as a result of aquafilter reconstruction is very evident. Yes, we can see this here. So here we have a similar story unfolds. Refilling of abandoned galleries has triggered uplift exceed. This is not enough. I mean, when we compare with the earthquakes, but here detect that surface uplift almost 10 centimeters, which is when we talk about cities areas, so it's a huge value. Okay, so other examples. So infrastructure monitoring, two last examples. Here, the first one, it's from the Mosul Dam in Iraq. What is interesting here? So the authors, researcher, use combination of multi-bands. If I could remember, it was yeah, we cannot see. It was X band, so Terrosar X, C band, and L band also. Acquisition indicated a creeping landslide. So after this analysis, what we can do, we can early detection enable engineers to inject some, I don't know, concrete and adjust reservoirs operation, which could have prevent a catastrophic failure of the region of this particular, the region's most important water storage facilities. And the last one example, the last one is also very interesting. This example involves the Rome metropolitan area. The author used more than, if I could remember, more than 100 or even 200 SAR as one data into a citywide, so we call like health scan of Rome's land surface. And the map shows that the runways at Fiumicino, I wrong this word, Fiumicino airport, are sinking up to 2 centimeters per year, which is also a lot. So their research has shown that we can use S1 data to monitoring the condition of road infrastructure. This study also proves that anyone, in my opinion also, with a laptop and open data can now monitoring the entire metropolis almost in real time. Yeah, and I think it Thursday, Professor Sandberg said that we live in golden age of SAR. Yes, I agree. So anyone is able to obtain data from particular anywhere on the Earth and analyze it, and this is truly amazing. So yeah, so thank you. I hope that the case studies I have shown have demonstrated how open satellite data and open source software enable us to address both scientific issue and society challenges. So thank you once again for your attention.
Thank you so much for a great talk. And our last talk today is from Katia, and she's gonna bring in some updates for NISAR.
I'm not sure about updates, but I will talk about why NISAR is great. This is, thank you for letting me share this with all of you. I know a lot of people are already familiar with NISAR. Let me see, I'm sorry. I hope I'm sharing my screen. Am I sharing my screen? Can you see my
Yes,
screen?
we can see your screen, but it's not in the presentation mode yet. It's got a slides on the side.
Is that good? All right.
Yeah, but let's
Okay, perfect. So yeah, I wanted to talk about for those of you who are very familiar with NISAR, probably these are going to be very familiar things that you've heard before. But for those who are not, I hope to get you excited about it and excited to work with the data. And the title of this presentation and the the point of this presentation is that NISAR is almost here. This is NISAR right here on the picture. It's an artist's depiction. It's going to be beautiful. That's what it's going to look like up in space in a very, very short time. So to move forward. So our launch is planned for 2025. It's a little bit funny, but I'm still not allowed to tell you exactly what the launch date is. But it's, I don't know how to word this, but it's really very, very, very soon. We are expected, what's going to happen after launch is we're going to get some first light images about 2 to 3 months after the launch. These are images that you will then start to be able to play with. Science operations, meaning that the satellite is going to be in the correct orbit, making consistent imagery. That should be available, or currently that is planned to be available 3 months after launch. Global products to level 2 are something that we're going to create. I'm going to talk about what level 2 is. I understand probably not everybody's familiar with that term, but basically the point is that NISAR is going to be a mission that is covering the entire globe, not just selected areas, but the entire globe with consistent spacing and sampling. I think my slides are timed for some reason. So it has a lot of different uses. And one important thing that we want to highlight as well is that there are cloud-based services that you can use based mostly at the Alaska Satellite Facility. So you'll be able to use a lot of tools, a lot of data and services that will facilitate your access and use, we hope, because this is going to be a data set that is an unprecedented amount of data. It's going to be larger than any other mission that we've had so far. So cloud-based services will be important. Just to show you what our mission timeline approximately looks like, after launch, the first few days and couple of weeks, perhaps, we're going to go through all the deployments, like deploying the antenna, making sure everything works. The first 3 months is called commissioning. The commissioning phase, meaning that we'll be getting into our science orbit, we'll be testing various functions of the satellite and so on. At some point toward the end of that 3 months, as I mentioned, we're going to start getting first light images. Those are going to be a little bit sporadic and not really ready for scientific use, but will be starting to see the data coming in. And then 3 months into the mission, about 3 months, is when we're going to start getting into our science operations phase. And that's going to go on for about 3 years. The first 5 months of the science operations phase, we're going to go through a period of science calval. So we're going to look at not just the simple quality of the images, but what do the images really mean for, sorry about this, what do the images really mean for science, and whether or not they meet the requirements. NISAR has a number of scientific requirements for how precise and how accurate the measurements should be to meet specific science goals. So we'll be looking at that during the calval period, and we'll be looking at that throughout the mission cycle, as you can see. And then it says here, of course, that about 3 years into the mission, we're going to go into decommissioning. So the mission lifetime, according to NASA, is about 3 years. This is, however, a joint project between NASA and the Indian Space and Research Organization. In fact, we are going to launch from India very soon. There is an instrument on board NISAR that is coming from us here at JPL, and one that is coming from India. And their mission timeline for NISAR is actually, again, sorry, these slides are switching on me. Their timeline for NISAR is actually 5 years. And on top of that, it is also true that NISAR has enough fuel to operate for about 8 years. So depending on a lot of things, perhaps like funding, we may be operating beyond this 3-year science operations phase. So let's hope for that. That will be really great. So I want to go over some things that are really special about this mission. First of all, it has a very wide swath. It's about 240 kilometers on all the modes. And so we're going to cover the entire globe at a 12-day repeat. So you'll be able to make 12-day interferograms anywhere. And depending on the latitude of your site, you will get 2 to 5 passes over a site over that period. We'll be getting data at ascending and descending geometries everywhere. And one thing that is also really interesting is that we're going to be a left-looking geometry. So most of the satellites that are operating now, most of the missions are right-looking. So because we're left-looking, we hope that will give us a chance to have a better resolution for 3D deformation. If you combine NISAR data with data from other missions, give us a little bit of more diversity in the observation geometry. So it should be very interesting too. Another thing that's special about NISAR is that this is an old map. This is a map of the observation plan from 2023. But even though it's not updated, I just wanted to share this with you to show how really truly tailored our observation plan is. Our science definition teams, both here and in India, have spent a lot of time really trying to figure out the best observation strategy for different regions on the Earth based on the science that is the most useful there. So there are going to be a lot of different kinds of data sets. There are going to be dual pole and quad pole observations for those who are interested in polarimetry. And all land is going to be covered every 12 days with a mode that enables what we've talked about here the most, which is, measuring deformation and InSAR measurement. So another thing to highlight is that the 2 instruments on board NISAR are L and S band. That means they operate at 2 different wavelengths. And there are going to be some places on Earth where those L and S band instruments are going to be recording at the same time. This is a completely unique data set. This has never happened before. So basically, there will be, during each orbital cycle, there will be about 100 terabytes of raw SAR data. It'll be very interesting. But there are these cowbell sites in Western North America, in South America, and in India and other places where L and S band observations will be made together. So that'll be an interesting data set that will enable some studies that we've never seen before. One thing, of course, it will enable a much better removal of the ionospheric effects that we expect, that we've talked about a lot during the short course. It will also probably enable other people who are actually interested in the ionosphere to study it. So it'll be a very unique data set that way. Some more characteristics. I think I mentioned everything here already. And just to emphasize that we do have a lot of capabilities here. We chose L-band as our mission, as our main wavelength, because it is able to penetrate through trees, through vegetation. So we're really hoping to observe a lot of places that are currently difficult to observe with C-band missions, with this L-band capability. So that's going to be exciting too, hopefully. There are a number of science and applications areas that are enabled by NISAR. These are just some of them. Some of them are really obvious. We've talked about them already a lot. Earthquakes, hydrology, but there are also, damage, groundwater flow. But there are also some newer areas of interest that NISAR makes possible. For example, measuring disturbance, measuring crops, biomass. Those are all things that we're also able to do. There are algorithms being developed for measuring soil moisture as well. These are more the application side of the of our mission. Rainfall, flooding, so oil spills, hurricanes, tornadoes. Many different things, and all of these things this is why, as many people have mentioned already in the last few days, it is true that we're living in the golden age of SAR. These are all things that will be available to you to look at and explore with our mission. NISAR also has an urgent response capability, so we're developing an interface where basically when a disaster happens, we can image it and make the data available more readily 5 hours after acquisition to product delivery, so that there will be a special archive for for urgent response, and we'll be able to deliver these products more quickly than regular data sets. So that's something to watch. We'll have more information on it as we start operating. This is a list of InSAR products that I wanted to go over with you. So I mentioned level 2 products. That's probably the most important thing. Those are the things that you're going to really focus on. So level 0 will be just radar raw data. And at level 1, we begin to see SLCs, single look complex images in radar coordinates. And from those, we will create a set of global level 2 products. Those are going to include polarimetric images that will be multi-looked and geocoded. There will be multi-looked and geocoded interferograms, unwrapped interferograms. So you will be able to simply, if you want an interferogram from NISAR, you'll be able to simply go and download an interferogram that you don't need to process and unwrap. However, I do want to point out that yesterday we talked a lot about batch processing. These interferograms that we're going to be providing are not going to be co-registered to each other. So they're going to be processed using sort of more the P2P, the point-to-point method, where each one of them will be processed and geocoded separately. So batch processing will still be very useful for a very useful function. You can still use GMTSAR to do that. I think GMTSAR is definitely going to respond and be responsive to NISAR and have capabilities for processing NISAR data. There will also be a completely new product that's called a geocoded SLC. I think we've also talked about that. So a single look complex image, but that is geocoded. It's a different kind of processing. It's a more flexible kind of processing. and hopefully it'll be a very useful product so that you could get SLCs that are geocoded already and combine them into whatever set of interferograms you want after that. An interesting thing to keep in mind is that there are going to be a lot of a whole pretty large set of level 3 and 4 products. So things that are kind of post-processed after the interferogram and other after the interferogram level and GCOV level. So each discipline, so different disciplines that we're covering are ecosystems, cryosphere, and solid earth, are going to create these level 3 and 4 products. Those will only be created in the areas that each discipline has identified as a validation area. So each discipline has a set of calibration and validation sites, as I mentioned, that they're going to be looking at. They're going to provide products for those particular sites. Those products include measurements of woody biomass, so you can look at what the biomass looks like in particular areas on the earth, vegetation disturbance, crop area, wetlands inundations. Those are all ecosystems with vegetation structure. Vegetation structure, as you can see, is a bit of an experimental product still. For solid earth, which is a lot of what we talked about in this short course, there will be ground deformation rates. So basically deformation time series. We'll produce time series over certain places on Earth as a validation product. I think change proxy or damage proxy maps will be produced as well. There will be several products for velocities for ice sheets and land ice and sea ice for cryosphere as well. So those will be available to the public, and they will also be stored at the ASF archive. That's the current plan. And we'll keep our community updated on when those become available. And in addition, there are other programs like the Satellite Needs Working Group that will be developing additional products like the soil moisture product that will be available, I think, globally, actually, and a global disturbance product and the Northern America deformation product. Those are managed by the OPERA project, and that's outside of the NISAR project. But those products will also be available to you to download. So a lot of really exciting data sets at all different levels that you can play with, you could validate, you can explore. If you want to take a look at our algorithms, so some of these products that I just went over that will be level 3 and 4 produced by the science team, the algorithms for creating those products live here. This is gitlab.com/NISAR science algorithms. So basically, you could go and download the code. Most of these, I think, are Jupyter notebooks at this point. These are Jupyter notebooks that explain how to make these level 3 and 4 products that are in this column here. And you can go and make them yourself. So you can point at any place on Earth and make those same time series in the exact same way that we're going to be making them for our CalVal areas. These are tools that are available to everybody, and you can easily download them and use them. What I want to say right now is that all of these tools are sort of experimental. They are a work in progress because just like with GMTSAR, we on the science team for NISAR are still developing these tools and making sure that we are ready to receive the incoming NISAR data. But for example, for solid earth, currently, you can run these tools with ARIA products from the ARIA project, deformation, wherever those exist in the world. You can download and run those and see how these tools are working and generate your own time series. So the backend for that particular part of the algorithms is MintPy. We mentioned MintPy when we talked about time series products. It does SBAS, and it also includes a bunch of these ionospheric and tropospheric corrections. So if you ever want to check, the point is GMTSAR already provides all these tools to you. You don't have to use any of this. But if you ever want to check the work that we're doing on the science team and tell us if we're doing a good job or if we're doing a bad job, you can check out these algorithms. These algorithms also do a validation, so a statistical analysis of the data set and a validation of the data set to tell you whether the data is good or not. So something else for you to check out and play around with is publicly available to everyone. If you want to, if you're interested in finding out more about what we're doing, you can sign up for two different things. So if you go to the NISAR webpage, nisar.jpl.nasa.gov, you can sign up for the community of practice, and that's for you if you're interested in receiving some regular updates about NISAR, some information. If you want to know about workshops and hackathons, or if you want to test our tools, test our algorithms, and provide some feedback, and provide feedback on our products, that's the place for you. Another option is, again, sorry for these slides, something got messed up about the format here, but another option is the early adopters, where you can, if you're the kind of person who's really focused on a particular project, a particular area of interest, and you can describe a specific need that you have for the NISAR data. And I mean, this is for early access. If you would like to have an early start into incorporating into your workflow. I know I did say it's true that NISAR is going to launch very, very soon, but you know, there's still about 3 months or more, a little bit more, until we start getting science-ready data. So it's not too late to become an early adopter. This way you can directly interact with our team and get some help with your particular project if you can identify a specific project that you're working on. And we will send you the most up-to-date example NISAR-like data products, and you can provide your feedback there as well. To conclude, I would just like to say that there are so many people that have put in so much work into the NISAR mission. This is just some of them. This is the science team, the project science team. On the next page, you'll see the science team from our Indian colleagues. But you know, our mission is primarily all the people who've contributed to it, and there has been a lot of great work that has been done, just like credits in a movie. Just would like you to share with you the names of our teams. Thank you, everybody.
Thank you, Katia. And I think this concludes our day 3 lecture. And David, do you want to have some concluding remarks?
Oh, I don't have anything specific. I know that Melissa's going to send some emails later on today about how to get the homework and where to find the book and where to look at the slides and the videos. But other than that, I've really enjoyed these talks. They're learning all about NISAR was wonderful. The infrastructure talk today was great too. They're all good. And for the students who are going to continue on with their instructors, you know, send them emails, send me emails. You know, this is a good time to communicate with anybody working with GMTSAR. So yeah, enjoy.
Yeah, and our first breakout session should be scheduled either tomorrow or on Friday. So your breakout group instructor should have already reached out to you, or probably they will reach out to you very soon on the exact time for meeting to get the homework started. And so if you end up using GMTSAR and have some great result, we always be very look forward to hear some news from you and what you find. And so thank you. And this concludes the plenary session.